Oh. So, can I start? Okay. And and I can use all four blackboards. Okay. Great. So, good afternoon, everyone. Coming to my seminar. I will be talking about uh, it- not invariance of knots and three manifolds, their connection to Chern-Simons gauge theory, and towards the end, I would like to give a statement of the volume conjecture for these invariance of knots. Okay. So, just to begin, I would like to just state that a knot is an embedding of a circle into a three manifold, which is closed and oriented and will usually be S3 unless stated otherwise. And a link is an embedding of some finite number of circles into a three manifold. Now, given a link, there is a notion of equivalence of links, which is called ambient isotopy. And what this means is that given two links, call them L1 and L2, and L2, there is a homotopy such that at each point of the homotopy, uh, this is an embedding. And usually, when one works with links, one of course draws some pictures. And so one usually works with a projection of these links onto a two-dimensional plane. And this projection is such that the only singularities that occur are of this type, which are resolved by drawing crossings, by differentiating between over and under crossings. And it is a well-known theorem of Reidemeister, which states that given two diagrams of two links, L1 and L2, are ambient isotopic if and only if one can go from one link diagram to the other by a finite number of the following moves. If L1, L2 are related by the following moves. So one can undo curls. Second, and the third one, which is the following. So these moves are called Reidemeister moves. And there is also a zeroth move which just says that I'm allowed to straighten curls. So straighten waves, I should call them. And okay, so this is all very good. And so when one is in search of invariants of links, what one does is one comes up with some quantity and then verifies that they are invariant under these moves, and then that tells us that this is indeed an invariant of the link. So the simplest example is probably what is called the linking number of two component links. So to define this, one needs to assign an orientation on links. So for example, if I have the Hopf link, I would to define this linking number unambiguously, I would like to have an orientation, and I would assign signs to crossings. So this is a positive crossing, and this would be a negative crossing. So according to this, I see that both of these crossings, if I'm not mistaken, are positive crossings, and the linking number is defined, linking number of a link, L, which has two components, is defined as the half of the sum of signs of all crossings. So this would have a linking number of +1. If these were not linked, so for example, like this, then this would have a linking number of 0. And one verifies that this is indeed an invariant, an invariant of ambient isotopy by verifying that this remains invariant under doing Reidemeister moves. And there is one other quantity which is going to be of interest, which is called the Reid of a link. And this is just the sum of signs of all intersections. So, however, unfortunately, this is not an invariant of ambient isotopy because this is not left invariant under the first move, because here we add a crossing, and doing this would increase or decrease the Reid by ±1. However, this is invariant under the second and the third moves, as one can verify. And invariance under the second and the third move is called regular isotopy. So this is not invariant of ambient isotopy, but is an invariant of regular isotopy. So invariance under the second and the third Reidemeister moves is called regular isotopy, and this is an invariant of regular isotopy. Yes.
In the condition, you take first a definition of ambient isotopy,
Yes, yes.
and then it will together.
Yes.
So if you let's say you list the condition 1, which is then what is the definition of regular isotopy?
So
and what is the part of the definition?
So I think, so in regular isotopy, one is not allowed to twist the links, right? So what one would do, I think, so one would have to introduce a notion of framing of links, and then require that the framings are left unchanged when doing this homotopy, also that additional condition. But in practice, it is easy to.
So it will be an embedding in terms of framing.
Yes, yes, of framed links, and at every point the framing is the same. Yes. Okay. So yes. So now aim of, so if I want to construct invariants of links, I want to construct quantities that are invariant under these moves. And for, okay. And so what I'm going to do is I'm going to, so given a diagram of links, I want to write it in terms of some tensors or matrices. So what I'm going to do is define the following. So yes, so I will write it down and then explain what it means. So for example, if I have a crossing of this sort, I would denote it like this. I will label the 4 edges and denote it by an 4 indexed object. So yes, and if I have a crossing of the other type, and I would also have, I would also assign a matrix, a quantity to maxima and minima. So this I would, and this I would call AB. And if I have just a strand running from up to down without any maxima or minima, this I would denote by a delta function. So now what I do is I take all these indices to be elements of some index set, and all of these numbers to be, so these are some complex numbers which depend on what index is on the edges. Now, given a diagram of a link, so for example, let's do the following. Let's do the following knot. This is, yes, okay. So this I would try to write in terms of these numbers, these matrices. And this, now once I have this, I will try to write it in terms of the symbols. So this is an R bar, A, B, C, D. This is another R bar, where this I would call E, F, G, H. Um, C, D. This is an R, D, G, H. This I will call I and J. And now I will write the M matrices. So one will come from here, M, A, F, M, B, E, and two will come from here, M, C, I, and M, J, H. And all of these repeated indices are summed over.
No, but n should have just two indices. Why?
No, because I made a mistake. There should be two m's. Yes, mj, h.
Should be up.
Yes, because it is a cup. Yes. So now this I will call tau of this knot. And I would like this tau to be an invariant of links. So that will impose some conditions on the r's, r bar, and these m's. So the first of those conditions, which comes from the zeroth move, is that that this should be equal to this, and this just means that m a I m I b is delta AB. So these upper indexed M matrix and the lower indexed M matrices are inverses of each other. Then at this point, I will only require this to be an invariant of regular isotopy. So at this point, I will not require it to be invariant under the first move. That can be taken care of later. It is just a kind of normalization. And under the second move, if I impose this to be equal to this, this tells me that R, AB, IJ, R bar, IJ, CD is equal to delta AC, delta BD. So R and R bar are also inverses of each other. And yes, and then there is this third move, which will give us the Yang-Baxter equation. So this third move in terms of these blobs will look like this. This is equal to this, which label A, B, C, D, E, F. And so this gives me, which I will actually write here, R, A, B, I, J, R, J, C, K, F, R, I, K, D, E is equal to R, A, I, D, E, R, B, C, I, J, and R, K, J, E, F. And this is the Yang-Baxter equation.
That is DK first. Yeah.
DK, yes, right. Thank you. And along with this, I have those two other conditions which just say that M and with upper and lower indices are inverses of each other, and these are inverses of each other. There is one more condition, which is that this is equal to this, which is equal to M A I R B J I C M J B. So this is a kind of compatibility condition between R and M. Okay. So, and one can think of other consistency conditions, but it turns out that these four conditions imply everything else. So now if I want an invariant of links to be constructed in this way, I need a solution of this set of equations. And there is a well-known machine which generates solutions like this. That comes from the theory of quantum groups, and I will talk a little bit about that. But before I move ahead, I would like to just mention one specific solution of these equations. With m equal to so with the following R m defined like this, the invariant tau k is what is known as the Kaufman bracket of a knot or a link. And this is related to the usual Jones polynomial, not colored, no colors yet. Yes. So this A is a complex number. So this is a polynomial in A. Yes. And now Laurent polynomial. Mhm. Yes, but now we recall that we had only required this to be invariant under regular isotopy, so this is still not invariant under the first Reidemeister move. However, with this form of the R and M matrices, one sees that the price of undoing a curl is a multiplication by A cubed, and earlier I mentioned the Reid of a link, which counts the number of curls in some sense. So to make an invariant of ambient isotopy, I can just normalize it appropriately by using the Reid of a diagram. So V L is a link, a variable equal to minus A cubed minus Reid of L, and then the Kaufman bracket. And indeed, the usual Jones polynomial, J, which is usually written in terms of a different variable Q, is just equal to this above thing with A set equal to Q to the minus 1 over 4. So this is the Jones polynomial that uh, now I would like to take a digression and talk about how this polynomial comes from Chern-Simons theory. And to do that, I will now, yes, to do that, I first write down the Chern-Simons action. Now this A is a connection on principal G bundle and is and yes, I mean these products are the wedge products.
Yes, but
I,
if principal G bubble, that is what A is a connection of G bubble, then it is valid where?
it's valued in the Lie algebra of G.
Yeah. So
And yes, there should be a trace.
okay.
Hmm. Yes. Yes, so A is a connection on the principal G bundle. G will be SU2, and it is a fact from geometric algebraic topology that says that when G is a connected, simply connected Lie group, then all principal bundles on a 3 manifold are trivial. So that means that this expression is globally well defined. So there is no ambiguities when defining this as the action. And to write down a gauge invariant uh, partition function, which I will write like this. So this normalization makes this gauge invariant, makes this exponential gauge invariant. K is an integer. And now, yes, okay. So now consider a link in M. I will just write it like this. L is a link in M. It has capital N components. And what I would like is to compute the Wilson loop operator for each of these loops, which they essentially are. And so for each of these links, Ki, A, I write down the Wilson loop, which is the trace, path ordered exponential over Ki, the gauge field. And this trace one has to take with respect to a representation of SU2. So here, so I have to specify which representation I am taking the trace with respect to. So I color each of these components with a representation of SU2. Yes, so Ki is colored with a representation Ri of SU2. Now I would like to compute the vacuum expectation value of the product of all the Wilson loop operators with respect to this partition function. And this is, yes, this, I have this. And however, when one actually tries to compute this integral, one has to take care of some regularizations. And generically, what happens when one tries to compute Wilson loops is that there is a summation, there is an integral of the following type. Uh, So when A is not equal to B, then by assumption, these are these are components of a link, so they do not intersect, and this integral is well defined. However, when they intersect, one needs to regularize this, and Witten has argued that a way of regularizing this integral is to talk about framed links, not just links. So I will briefly describe what a framed link is. So given a link, one picks a normal vector field on the link, which is called its framing. And one can, so one, if these normal vectors are appropriately normalized, then one can trace out the path along the tips of these vectors. And so starting with a not k, I get a k prime, which wraps around the first knot a certain number of times depending on the framing. And yes, so given a framing, I can always construct this. So when a is equal to b, instead of doing an integral over ka and ka, I do an integral over ka and ka prime, which is determined by the framing. This gets rid of the there is this subtlety because of which one has to talk about framings on links. But once I have this expectation value, uh, then yes, and when so if all of these colorings are the two-dimensional spin half representation of SU2, then this expectation value is equal to the Jones polynomial of the link L evaluated at Q equal to exponential of 2 pi I divided by K plus 2, where this K is the Chern-Simons level. Yeah. Here, if I pick all of the representations to be this two-dimensional spin half representation of SU2, then this is the Jones polynomial that was described there. However, generically, these expectations value define a colored Jones polynomial of the link, evaluated once again at this root of unity. Now, in the remaining time, I would like to talk about which solution of this Yang-Baxter system of equations gives the colored Jones polynomials of links.
Sorry, what is omega when I missed it in up there minus yeah?
This?
Omega when?
This is the right of a link, which I think I erased.
Oh, sorry, I missed it. Sorry.
But the right is just the
Okay, okay.
sum of crossings. So, I mean, one has to do a computation to verify that this is indeed the case, but this is indeed the case. And now I will very quickly talk about the solution to these how solutions to these equations can be constructed, which give the colored Jones polynomials. So now, before I start talking about that, I would like to think about what happens with this solution, which gives me the regular uncolored Jones polynomial, when a is equal to 1. So when a is equal to 1, then R, A, B, C, D, this is equal to, when A is equal to 1, this is just I of epsilon, where epsilon is the antisymmetric tensor of two components. So this is equal to epsilon AB plus delta AC delta BD. And now, once again, when A is equal to 1, note that R and R bar, both of them have the same form. So written in terms of skeins, I would write this relation as yes, it should be CD. Thank you. Yes. So now if I write this equation down in terms of knot diagrams, I would write it as follows. So this R ABCD is equal to A cup cap plus A inverse and two of these guys. So when the crossing is the opposite, it would be A inverse with the cup cap there plus A of these delta functions. So when A is equal to 1, one cannot tell apart an overcrossing and an undercrossing. So it is, this can be done properly, but at the level of these diagrams, it is reasonable to assume that this R matrix is the following. And when I look at this, I am reminded of spinors. And so this is nothing but an identity of SL2 invariant symbols, where SL2 is in the fundamental representation. So with this as a sort of motivation, I will say that if I want the usual Jones polynomial at different values of A, I would have to twist this SL2 in a certain way. And that twist is exactly the quantum SL2 group. However, I will, to work with, to talk about these, it is usually better computationally to pass on to the dual, which is the quantum, the, the quantum SL2 Lie algebra, which is generated by the following symbols, KEF, and the following, I'm sorry, this. I will describe this. So this, I mean, I will use the other H, X, and Y. We've generated by these and with the following modulo the following relations. Where these square brackets denote the following operation. And one also has to consider a representation of this as of this Lie algebra. So in the case of the usual SL2 Lie algebra, we know about the uh, finite dimensional representations, and yes, and so for each k, there is a finite dimensional complex representation, which is given by, so this has basis there, 2m plus 1, and the representation is given by the following relations. And so these are the representations of the usual SL2 Lie algebra. But when one does this twisting, and this twisting parameter is usually a root of unity, one finds out that these representations do not go to infinity but only go to R. And so these are the only irreducible representations. And now these square brackets are to be interpreted in this way. Okay, so once one has these relations and the representation, one looks for an R matrix, and to do it, one chooses an ansatz. So here I should say that I define K to be this. So one guesses this form of the R matrix and then substitutes this into the Yang-Baxter equation to find out what these coefficients are. And however, there is k is q to the h. Ah, yes, this is k composed with itself a times.
Okay, so it's a power.
Yeah, it's a power. Yes, yes. So what one does is use this ansatz in the Yang-Baxter equation and compute these coefficients. One gets a formula, but that is not super interesting at this stage. But there is a slight problem, because to get from this representation theory R matrix to the knot theory R matrix, one has to do a permutation. So after applying this, one has to permute the two sides of the two things on the opposite sides of the tensor product. So the knot theory R matrix is a permutation composed with this R flip. And indeed, in the case where and indeed at this stage, if one thinks about taking the semi-classical limit of q going to 1, this R flip reduce. So in this limit, so these coefficients vanish unless n is equal to 0. And in this limit, this k goes to the identity. So this here, what one gets is just an identity, tensor identity, and composing it with a permutation operator like this, one gets this crossed thing. So, I mean, with this solution, it can be verified that taking the semi-classical limit reproduces the relation that one gets from the usual SL2 matrix, which evaluates the Jones polynomial at q equal to 1. Right. So yes, so with R this and m equal to k squared, with this one can verify that these relations hold with this value of R and this value of m. And then one proceeds in the exact same case. So given a link diagram, each of the components are colored with a representation of this quantum SL2 Lie algebra, and then the invariant is computed with this R matrix and the following form of M. Which, I mean, in general gets quite hard to do, but yes. So that is the definition of these. Yes, I think I will also write this down. So given a link with this invariant computed with the following form of R and M matrices, this is the colored Jones polynomial for L evaluated at q equal to e to the 2 pi I over R. So, and that colored Jones polynomial and this colored Jones polynomial are, one can show that these are the same. And to show it, one usually uses the skein relations of these polynomials and shows that they satisfy the same skein relations. So they must be the same polynomial when evaluated on knots. Now, the last thing I would like to do is I would like to state a conjecture regarding some asymptotic limit of this guy, and that is the volume conjecture. So given a link L in S3, this link L is hyperbolic if S3 minus L admits a metric of constant negative scalar curvature. Now, so there are a lot of examples of hyperbolic links. The figure eight knot, for example, is a hyperbolic link. And yes. So now, if L is a hyperbolic link, then one has the following limit. Up to factors of I pi squared. Yes. So this, and this here, so this is the volume of the knot complement evaluated with respect to the hyperbolic link, and this is the Chern-Simons form of the, but this of the Levi-Civita connection induced by the hyperbolic metric. And so yeah, so this Chern-Simons has nothing to do with the principal G bundle or any of this business here. Yeah.
So here you have just polynomials.
Yes.
And in right hand side you say you take forms.
So these are numbers. This is a complex number. So yeah. So this.
The first part is volume of.
Yes. Volume of the knot complement with respect to the hyperbolic metric.
Okay. So the JN, I mean, in general, depends on the representation.
Yes. So for SU2, all of these representations are just represented by integers, and all of the links are colored with the same representation, capital N. But so here I was using capital N for the number of links. This has nothing to do with that.
No.
Yes.
That one labels the representation of
Yes. So all the components are labeled with the same representation because in the end I'm interested in this limit. Yes. Yes.
So you have angles roots in the same
Yes, exactly. I mean this because in the end I'm interested in taking the limit of n going to infinity. So yeah.
So given that last usable representation, which is an improved representation of non-clear boundaries.
I'm sorry.
Given the last representation for which the numbers don't vanish or not?
Yes, because when one computes, so if I so it indeed it turns out that if I color any of my links with this last representation R, then the Jones polynomial would vanish.
So are you using that the last non-trivial representation?
E,
So what is this GM? Isn't GM correspondence like which what representation is there in the GM?
mhm. Yes. So um, hmm. Hmm. I think it should be the some yeah it should not be the trivial representation. I think maybe I'm missing something, missed something when copying this. Uh,
It just is not the like n-dimensional representation of
uh, no, well, in this sense, one has to label it with the representation of the quantum algebra, and when evaluating the Jones polynomial with this last representation, if any of the components are colored with the last representation, then this evaluates to 0. So there should be some, I think I'm missing something, but
Before, when we find the evolution loops, the traces were taken with respect to the
SU2 representations, yes.
but it turns out that if I receive the maximum representation of the quantum SL2, those are identical ones.
Hmm. 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 So, yes, there is some subtlety which I'm not sure of. Yes. So, but yeah. So just to end the talk, I should say that this volume conjecture has been proven for certain specific cases of knots. So, figure 8 knots and torus knots, for example, it is known that this is true. But generically, for any link, this remains an open problem.
What are the motivations for this? Is it something like then compute this percentage by some pseudo current which does not belong to a single connections or
Yes, indeed. So yes, indeed. So this can be thought of as a kind of semi-classical limit of the Wilson loop operator, the vacuum expectation value of the Wilson loop.
This Wilson loops should be a heavy objects in this limit, so representations should be big. But why this particular limit? For example, why you cannot send the size of representation with a different speed? For example, put some g alpha n and add some extra parameters. So what will change in this case?
I think the reason why people take this limit is because this is easy to compute.
What kind of computation would this be and what simplifies in this particular?
No, I'm saying that the choice of the colorings n, this, so taking all of the components of the link to have the same color, and that color is the same as that is, yeah, that is related to the root of unity value. This, I think, is because the computations simplify, uh, but I'm not sure what happens when one changes the labelings or colorings.
No comments, questions? Okay, so not we thank you.